I'm here for the rest of the semester.
Oh, I thought you were here like every report.
Oh, no.
That would be nice, huh? All that time on the brain.
All right. So let me start by reminding you what we did last time. So last time we proved this theorem of Takeuchi that says that if you have a graded connected bialgebra, then the antipode comes for free. So any graded connected bialgebra is actually a Hopf algebra. And Takeuchi actually gives us an explicit formula for the antipode, which looks like this. Okay. Now, I want to make a couple of comments about this. So, basically, what happened is the video ran out. And when the video ran out last time, I explained what this formula was really about, or how it's easier than it might seem when you look at it. So let me just make a couple of comments now that we're on tape again. So one thing to make a comment is that this thing right here this thing is nothing but the convolution product of pi with itself n times. Okay. So n times. So I actually wrote this as pi star n. Okay, so it's like pi to the n, but under the convolution product. And so then if you look at it, the formula looks a lot easier. It just says that the antipode is the sum over n greater than or equal to 0 of -1 to the n, pi to the n. Okay? And so really an easier way of understanding the proof is the following. Remember that you want the antipode to be the inverse of I under the convolution product. Okay, so let me say that with regards to the convolution product, so with respect with respect to the convolution product let me put this in quotation marks. I gave you a proof last time, and I'm going to give you an explanation, a quick explanation of what that proof is about and why it's maybe in this notation it'll be a little bit easier to see. The antipode is supposed to be the inverse of I under the convolution product, where I is just the identity function. Okay? Now, I happens to be pi plus u epsilon. Okay? And not only that, u epsilon is actually the one of convolution. Right? This is the multiplicative identity with respect to the convolution product. So let me write it as 1. Okay. And again, here we have to be very careful what the symbol 1 means. But as I just said, 1 I mean this. Okay. But 1 is really the one under the convolution product, and so all I have to do is compute 1 plus pi inverse, and we know how to do that. This is just the sum. I mean, this is just a geometric series. And we just get minus 1 to the n, pi to the n. That's what this geometric series is. Except, let me make a couple of comments. First of all, everything is under the convolution product, so when I write pi to the n, I really mean the nth convolution product of pi. And so I need to put a star here. Okay. And the second thing that makes you a little bit nervous, yeah, question?
So, what makes me a little nervous about that there is, why can we just assert this formal equality, especially when we're using an identity that's developed under what I'm calling polynomial multiplication?
Right. So what might be making you nervous is that this is not the context where you usually use the geometric series, and for the first time you saw it was in a calculus or an analysis where pi was supposed to be some real number less than 1 in its absolute value. Okay. But what I claim is that actually this is just a formal equation that holds true in any algebra as long as this thing makes sense. And the thing to remember about this is that we remarked last time that this is, even though this looks like an infinite sum, this is actually a finite sum. And the reason for that is that pi star to the n starts by taking the n minus first coproduct. Okay? And so we saw that from some point on, I mean let me say it like this. For a fixed h, this is equal to 0 for all large enough n. This is what we remarked last time. And so this is actually a finite sum for any particular element of the Hopf algebra. If you plug in h for a particular h, eventually all of these terms are going to be 0. You get a finite sum. And so to check that the inverse of this is this, all you have to do is just multiply this thing by 1 plus pi and show that you get 1. Okay? And my claim is that the motivation is that this holds in any algebra as long as this sum is going to be finite. And the proof is what we did last time. Okay? So, I mean, if you want the rigorous justification of this, it's what we did last time, but the motivation for this is just that we're just imitating a geometric series. Okay? Krista asked me last time, how did anybody think of this formula, which looks so complicated? And I just want to make the point that actually it's just that this formula, which maybe you're used to it in a different context, but you have to wonder, well, does it hold in this context? And it turns out that it does. And that's what we showed last time. So, and that's why I write in quotation marks proof, and then the details we did them last time. Okay? But that's really what's going on. Okay? And in particular, let me make another comment about this, which is the following. Let's say that a Bialgebra H is conilpotent if for any element of the Bialgebra there exists an integer n greater than or equal to 0 such that the nth coproduct of H is equal to 0. Okay? And the next claim that I want to make is that this exact proof works in exactly the same way for any conilpotent Bialgebra. Okay? Because really the only subtlety that comes up in this argument is that this should be a finite sum for any H. Okay? But again, think about it. If you plug in H here, what you're doing is plugging in H here, and you start by saying delta of a large number of H, and so you're going to get 0. Okay? So whenever your Bialgebra is conilpotent, it is true that this is going to be a finite sum for any H in your Bialgebra, and therefore you can make the same argument. Okay? And so in fact, I can make a stronger statement that any conilpotent Bialgebra is a Hopf algebra.
Okay. So just to clarify, are you saying that, so you're saying stronger because there are fewer Bialgebras, so not all graded connected Bialgebras are done?
That's right. So there are conilpotent Bialgebras that are not graded connected. But, I mean, if you look at how we proved it, what we did is that we proved that any graded connected Bialgebra had this property. And, therefore, this argument held. So, graded connected implies conilpotent, but not the other way around. And my claim is that the exact same proof that I did works in exactly the same way for conilpotent Bialgebras.
What we showed the last time was more that if you take a large enough n, then you have the delta of the n has a field constant term somewhere in the tensor product, and then the pi cancels that. Not that that thing itself is potentially equal to 0. So I feel like we've had some deltas like where just delta h
Yeah.
where it never would get to 0 on its own.
Yeah, you're right. Actually, I'm being what I'm saying is not precise. So let me say what's really true. So if you were graded connected, then what we showed is that when you take large iterations of the coproduct, we got constants, and those constants were killed by pi. And for that reason, this was equal to 0. And so what I really should be saying now is that if the Bialgebra is conilpotent, then maybe this is even easier. Okay? And this because you don't even need the pi, this is going to work out, and you're going to get the same result. So maybe what I mean is not to say that one is stronger than the other, but that they're both true, and that the same proof works for both. Okay. Now, let me make another remark about this, which is that I like this formula very much. I like this theorem very much. But it's a bit of a hairy formula to use. Okay? And so let me make the comment that it's nice to have Takeuchi's formula, know, it's a first of all, it tells you that the antipode comes for free, and second of all, it even tells you exactly what that antipode needs to be. But that formula doesn't always give you an easy answer. The resulting formula for the antipode can be unnecessarily complicated or even unenlightening. And that's what I want to illustrate to you now. And so I want to illustrate this to you in a concrete example. So let's try to use Takeuchi's formula in a nice, easy, simple bialgebra that we know that is graded and connected. Okay. What's the simplest example you can think of a graded, connected bialgebra that we know? I'm sorry? Easier than that. K of x. Right? You're anticipating what I'm going to do next, which is to do it for posets. But let's do an easier example first. Here's a bialgebra that is graded because it's graded by the degree of the polynomials, and it's connected because the degree 0 things are the constants, which is k. Okay. Let's try to apply Takeuchi's formula. Okay. So we're supposed to do this. We're supposed to do S is the sum minus 1 to the n minus 1 we're supposed to do this, right? And so let's try to evaluate this at something. Okay. For example, I mean, we need to evaluate the antipode in the whole bialgebra, so we should evaluate it for every basis element. So let's see what happens when we evaluate x to the capital N. Okay. So we need to compute this right-hand side, and that means the first thing we should do is compute this coproduct. Okay. So first of all, we are going to compute this. And well, at least we know what delta of x to the a is, right? We've done this, and we got that is the sum over all pairs I plus j equal to a of a choose I, x to the I, tensor x to the j. We computed this, and now let's apply the coproduct to this, just to see if we see a pattern. So when we take the coproduct of this, remember that we have two options. We can apply the coproduct to the left-hand side, or we can apply the coproduct to the right-hand side. And this is the coassociativity, which tells you that you can go one way or the other way in that commutative diagram. Okay, so maybe I'll do this. Maybe I'll apply the coproduct to the right-hand side. Sorry, it should be delta, right? What's delta of x to the j? Well, we know what this is, right? This is some, let's say, over k plus L equal to j of j choose k x to the k tensor x to the And so what are we doing here? We're summing over all choices of I, j, k, and l such that I plus j is equal to a and k plus l is equal to j. Okay? And if you look at what we're doing, actually, we're just looking at all the ways of, j is just k plus l, right? And so we're just looking at all the ways of choosing I, k, and l such that I plus k plus l is equal to a. And then j is fixed. J is just going to be k plus l. Okay? And so what I'm going to get, I can move constants around. So choose I as a constant, j choose k as a constant, and I get x to the I tensor, x to the k tensor, x to the l. Okay. Now, okay, well, what is j? I shouldn't have the letter j here because I don't have it here, right? So j is what? You sounded like you were going to say something different, which is also true.
I plus L?
Or j is, you can say j is k plus l, or you can say j is a minus I. Which one should we use? It doesn't really matter. They're both true. Then maybe I'll use a minus I. Okay? Now, does anybody recognize this thing? A choose I, a minus I choose k. I'm sorry? So this is what's called a multinomial coefficient. And this thing, by definition, this is called a choose I, comma, k, comma, l. What is this? Well, first let's go back to what is a choose I. A choose I says you have a elements, you choose I of them, and you don't choose the remaining a minus I. What is this symbol? This symbol says you have a elements, you choose I of them and put them on one basket, you choose k of them and put it on a second basket, and the other l you put them in the third basket. That's what this means. Okay. How do we know that this is equal to this? Well, how can you take a elements and put I in one basket, k in the second, l in the third? You could say, first, let me choose I of the elements and put them in my first basket. And then out of the remaining a minus I, choose k of them to put in the second basket. And then the rest you put in the third basket. Okay, so that's why these two things are equal to each other.
So that last one is just L choose L.
Mm-hmm. Now let me write this in a couple of ways. So let me write this down. So number of ways of putting splitting an A set. So by this I mean a set of size A into an I set, a K set, and an L set. Okay. But there's also a formula for this, which we get. We have this formula for A choose I that A choose I is this: A factorial divided by I factorial, A minus I factorial, and A minus I choose K is A minus I factorial divided by K factorial, and then A minus I minus K is L. Okay. And so this cancels with this, and I just get A factorial over I factorial, K factorial, L factorial. And so I get, in summary, I get that the second coproduct of x to the a is equal to the sum over all ways of writing a as I plus k plus l, and then doing this. IKL x to the I tensor x to the k tensor x to the L. Okay, that's the second coproduct. And given this, you can probably guess what the nth coproduct is going to be. Actually, we want to apply delta of n minus 1 of x to the n, and so you can guess what that is. We're going to get sum over all the ways of writing the number n as I1 plus etc. plus I lowercase n. And then I get n choose I1, comma, I2, comma, In. And then I get x to the I1, tensor x to the I2, tensor x to the In. Okay? And so this gives us a formula for the first part of what we need to do. Okay? Which is this. All right. So having done that, now we need to apply pi. Or rather, pi tensor n, right? And to do that, we need to figure out what pi does. Okay? So pi, okay, we know the formula. It's I minus u epsilon. But let me make the point that I made last time, which is that that's not really the way you want to think about this. First of all, remember that pi takes h to h, right? And so you just have to say what pi does to a basis element. Let's say x to the a. And I give you a description of what pi does, and this is the way that you should think about computing pi. You shouldn't be plugging in I minus u epsilon. It should just be, I mean, remember that, I just leaves you alone. Okay, so pi of x to the a, well, I of x to the a is just x to the a. And we talked about how u epsilon is just taking the degree 0 part of what you have. Okay? And so what pi does is that it takes your element and it drops the degree 0 component. Okay? So what happens when you drop the degree 0 component of x to the a? Well, usually nothing, because there's no degree 0 anything here. There's only one case. So if a is greater than or equal to 1, then there's no degree 0 here, and there's nothing you're dropping. Okay? But if a is 1, sorry, if a is 0, then here we get pi of 1, and 1 is of degree 0. And so that guy gets killed, and so you get 0. That's what pi does. It just leaves a monomial alone unless it's a constant. The constant monomial. And so, given that, we can now figure out what this part of the formula does. So what is this? Pi tensor n delta n minus 1 x to the n. What does this do? Well, we know what this is. Sum over the ways of writing n as a sum of non-negative integers, and choose I1 up to In, x to the I1, I get this, right? And now what this does is that it applies pi to each one of these things. And so that means that usually it's going to leave this alone. The only exception is that maybe some of these i's are 0. And whenever one of the i's is 0, then the corresponding pi is going to kill it, and it's going to make that polynomial disappear. So what is the effect of doing this? You get all the same terms, except that you just need to make sure that none of the i's is equal to 0. As long as they're all greater than or equal to 1, they survive. So you get this thing. Okay? So that means that we know now what this part of the formula is. Okay? Finally, we need to apply m to the n minus 1. Okay? So let me just do that here. Let me apply m to the n minus 1 in front. Okay? And so that's just going to put a m to the n minus 1 here. Okay? And that means that I'm applying m to the n minus 1 to this guy. Now what does m to the n minus 1 do? Remember, m is just multiplication. And so what m to the n minus 1 does is that it takes this tensor and it just multiplies all the elements. Okay? So that means that what I get is equal to sum over I1 plus dot 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 plus In equal to n, all the ij's greater than or equal to 1, and choose I1 up to ij, and then I multiply x to the I1, x to the I2, up to x to the In. What happens when you multiply those? You get x to the I1 plus I2 plus dot 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 plus In, which is just x to the n. Right? Okay? And so this is getting, we're getting somewhere. We have some expression.
Why does it go from I1 to ij? And
Oh, I meant In here. Thank you. But all the ij's should be greater than or equal to 1. By the way, what would happen if we didn't have this condition? What would this sum be? You guys know? One thing you'll notice is that x to the n just falls out of this, right? X to the n you can factor out. So we're saying, right, so this is partitioning a set of size n into a set of size I1, a set of size I2, up to a set of size In, okay, for a fixed i's. If you sum over all the possibilities of i's, you're just looking at the ways of splitting up a set of size big N into small n sets. And that is just small n plus 1 to the big N. Because you get to say, wait, let me write instead of, because let me write what I'm saying. You can see that I'm taking the excuse to teach you some combinatorics. I mean, what we're about to do isn't exactly relevant, but it's kind of relevant and it's good for you to know. So what happens if what I'm saying is this. We're considering this thing. This says split the set 1 up to n into sets of size I1 up to In. Now, if you sum over all possible sizes, really, what you're saying is, what is the number of ways of splitting this into n sets, and you don't really care what the sizes of those sets are, because you're summing over all possible sizes of those sets. So what is the number of ways of splitting the set 1, 2, up to capital N into small n sets? Well, you just have to say, take your first element. Where do you put it? You have lower n options. Take your second element. You have lower n options. Take your third element. You have lower n options. For each one of the elements, you have n sets to put it in. So this is just n to the n.
So the partitions, the order matters, but the n elements aren't distinguishable, are they? Capital N elements?
The capital N elements are distinguishable, and in the partition, the order matters.
In terms of what we're looking at, I guess I'm not clear on why. Yeah, okay, I guess.
I mean, let me go back and repeat what I said a little bit earlier, which is this is not exactly relevant, because in that sum over there, we have the ij is greater than or equal to 1. And if we didn't have that, then we would get a really simple formula. But we have that, and so we have to deal with that problem. But the reason that I wanted to say this actually is that I want to write down something that maybe you've seen, maybe you haven't seen, which is called the multinomial theorem, which you know for 2 variables, but it's good to know it for n variables. Which is that if you do this, okay, so we take the same sum, but now in front of each term, we put the monomial x1 to the i1 up to xn to the in. What we're going to get is precisely the expansion of x1 plus dot 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 plus xn to the capital N. That's an important formula that you might call it combinatorics, you might call it analysis, whatever you want to call it, algebra. But you know, it's just a very important formula that says how do you take a multinomial, some linear function to, some sum of things to the nth power, and this is what comes out. And whatever formula, whatever proof you like of the binomial theorem, also works here. If you've never proved this, I think you should. That gives me a different proof of this formula, right? Which is, say, set all the xi is equal to 1. Then this disappears. And here I get 1 plus 1 plus 1 plus 1 to the n. So I get n to the n. OK. Yeah? OK. So that... Yeah. So like I said, if you know any proof of the binomial theorem, you can find the analogous proof of the multinomial theorem. So in particular, there is a simple bijective proof of the binomial theorem. And think about it a little bit, and you'll see that it also works here. Any proof that you know of the binomial theorem is going to work here. Like induction, anything. OK. But anyway, so that's a bit of an aside, because I think that's a useful formula that you should know. But now you should be bummed that we cannot use it, because we have this extra condition, that the I should be greater than or equal to 1, and so we have a little bit more work to do. But this gives you an indication that probably we can deal with this. If we know how to do that, we can probably do this. Okay. We're not quite done, right? Because now we need to sum over n greater than or equal to 0. So the formula that we get is sum n greater than or equal to 0, sum minus 1 to the, yeah. So minus 1 to the, yeah, this was supposed to be minus 1 to the n, like Takeuchi tells us. And so I should have sum n greater than or equal to 0, minus 1 to the n. We get this. Okay. Do we agree? So that's a formula for the antipode. Okay. So let me now erase all this stuff. So here, there's one of two things you could do. You could say, okay, I have a formula for the antipode, I'm done. Took me a little bit of work, but I used Takeuchi's formula, and this is what I got. But you might also say, you know, it's kind of a complicated formula, and maybe I can simplify it. And especially if you like generating functions, or if you like manipulating formal power series, then actually you might want to say, I think I can do more with this. Okay, and so that is exactly what we're going to do. I'm going to show you that you can simplify this a lot.
I think that's the capital.
It isn't actually, which is very strange. That's a very good point. And is that, wait. Oh, no. No, you're right. Yeah. No, you're right. So this is our formula, okay? Now, what you'll notice about this formula, actually, is that this is just a scalar times x to the n, right? We have the x to the n, and then the rest is some big sum. It's a number. And we would like to know what that number is. So we're going to figure it out. So we're just going to take this formula and run with it, okay? So let me do a couple of things. So first, let me multiply this out like I did earlier. Okay, so this is n factorial over I1 factorial up to In factorial x to the n. Okay. Now, I can pull this out, n factorial x to the n sum n greater than or equal to 0 minus 1 to the n sum this is what I get, right? And now I would like to take this thing and make a little observation here, which is the following. So what happens if you do the following thing? What happens if you take let's take this series, okay, and raise it to the nth power. What is the coefficient of x to the capital N here? So this symbol means coefficient of x to the n. Well, what is it? It's, maybe because this is the first time that we do this, let's do this a little bit slowly. Okay, so By the way, what is this series that I just erased? X to the 1 over 1 factorial plus x to the 2 over 2 factorial plus etc. It's exactly e to the x minus 1, right? That's the series for e to the x minus 1. But now let me write it like this. So e to the x minus 1 is sum from, for I greater than or equal to 1, of x to the I over I factorial to the n, right? So now I'm going to do something a little bit funny, which is that instead of raising this to the n, I'm just going to write the same thing n times and use a different letter each time. Okay? There's no problem with that, right? Each one of these sums is e to the x minus 1, and I have n of them, so I have this. Okay, but what happens when you multiply n series like this? How can you get an x to the n? Well, you get an x to the n whenever you manage to pick an I1 here, an I2 here, up to an In here, which add up to capital N. So I have to look at the ways of choosing a term I1 greater than or equal to 1, a term I2 greater than or equal to 1, up to a term In greater than or equal to 1, such that when I multiply x to the I1 up to x to the In, I get x to the capital N. So, in other words, this should add up to n. And then what am I going to get? I'm going to get x to the I1 over I1 factorial, x to the I2 over I2 factorial, x to the In over In factorial. In other words, I get this thing that I have here. Do we agree? So that means that what's my antipode? Well, I have the n factorial x to the n. That's always there. And then I get sum over n greater than or equal to 0 of minus 1 to the n. And then I get this term, which is the coefficient of x to the n in e to the x minus 1 to the n. Okay? Now, I'm taking I have a sum of things of the form take the coefficient of x to the n in this. And that's the same thing as taking the coefficient of x to the n in the sum. So I can take the coefficient of x to the n in the sum. Sum n greater than or equal to 0 minus 1 to the n e to the x minus 1 to the n. Okay? Do we like this sum? It's not a bad sum, right? Because how much is sum n greater than or equal to 0 of this? Well, let me just bring the minus 1 into here. I get 1 minus e to the x to the n. So what's this? This is a geometric series, right? So this is the geometric series sum of something to the n. It's 1 minus this. So what's this? This is 1 over 1 minus 1 is 0, minus e to the x. So this is just e to the minus x. And so really what I'm asking you to do is take the coefficient of x to the n in e to the minus x. Okay. What is the coefficient of x to the n in e to the minus x? So we know the Taylor series of e to the minus x. Right? This is e to the minus x is just sum of I greater than or equal to 0 minus x to the I. Okay? And so if you want to get an x to the n, by a factorial. And so the coefficient of x to the n is, so we leave this here, we leave this here. The coefficient of x to the n is minus 1 to the n over n factorial. And so what do we get? We get minus x to the n. Okay. So we clearly shouldn't have stopped back there. We just should show that the antipode evaluated at x to the n is minus x to the n. A beautiful formula, and then I want to make 2 points about this. First of all, the first point, that Takeuchi gives you something, but actually that something might be very misleading, because you might get this and think, wow, this is a really complicated antipode. You know? But sometimes you can take what Takeuchi's formula gave you and just recognize it as something simpler. And actually, you can get a very nice answer. By the way, did we know this? Did we know that this was the antipode? Can you think of an easier proof?
I think we worked it out as not constructing this example, but it showed it worked.
That's right. So the thing is, we know that the antipode actually behaves nicely multiplicatively. So now that I mean, this was not the easiest way of seeing this answer, but actually let's do an easier proof now. How can we argue that s of x is minus x? Because I mean, yeah, there's different things we could do, but what do we need? We need that. We try to write it in Sweeler notation. So we need that. We need that the convolution of S and I should be 1 in convolution. In other words, we need that the sum of S of H1, H2 should be H. Should be U epsilon of H for any H. So in particular, for H equals X, we know that delta of x is 1 tensor x plus x tensor 1. And so we need that s of 1 x plus x s of 1 should be yeah, thank you. Should be this thing evaluated at x is 0, right? And s of 1 we know is 1, because that's always true for the antipode. So s of x is minus x. So s of x is easy to compute. And now we can just say, and s of u v is equal to s of v s of u. Which means that s of x squared, or in general, s of x to the n is going to be s of x to the n, and therefore you get minus x to the n. Okay? And so let me, give me just a second, let me make the 2 points that I want to make. So, in conclusion, Takeuchi gives you a formula but that formula may be far from optimal. And to get an optimal formula, you might either simplify what Takeuchi gives you, or you might just think of something else. Be clever in some other way. Okay. In this example, I think it's clear that Takeuchi's formula was not the way to go. Because I just gave you a much easier proof of the same formula. Really, there was a couple of reasons why I wanted to do this. First, to make the point, I think pretty eloquently, that Takeuchi really might not be the shortest answer, and sometimes it's just not really how you want to proceed. But I also wanted the excuse to do some combinatorics like this, which we're going to need later on. Combinatorics slash analysis slash what is called generating functionology. But yeah, so hopefully that shows you some of the pros and cons of Takeuchi's formula. But let me just say that a general problem of interest is to give an optimal formula for the antipode. The antipode of a Hopf algebra. And what might we mean by optimal here? Well, we don't mean what Takeuchi gave us. So how do we make precise what optimal means? It should be closed form. And one thing that will happen in almost every Hopf algebra that we've seen, there's a nice distinguished basis. And you don't really want a formula that has cancellation in it. You don't want to see. I mean, like in this formula that I gave you, we saw there's like n to the n terms, but really they all cancel each other and you get a single term. And so what you want is no cancellation and no repeated terms. Now, naturally, that depends on what basis you're working with, and so let me I put quotation marks here because part of the game here is also trying to figure out a good basis to work with. And in some cases, you might have several different formulas according to what basis you're working with. But this is a general problem of interest that you want to solve for any Hopf algebra that you have in your hands. And let me make the point that sometimes this is not known. Sometimes we don't know how to do this, and sometimes we do. There's two other examples where either you know or should know by midnight how to do this. Right? So graphs and permutations. Now, so this is in your homework 3. I'm asking you to give simple formulas for the antipodes of two particular Hopf algebras. And so you should look for formulas that have no repeated terms, no cancellation. Okay. Let me make a point, because there was actually I got an email from somebody about this question. The first day of class I defined one Hopf algebra of permutations. In the homework I'm talking about a different thing. Okay, so make sure that you realize that that is different. That's why I'm putting quotation marks, because I'm not being very precise about what it is. But in the homework, I'm very precise about what these two things are, and that's what you need to compute. Yeah?
The phrasing on 5b seems to suggest that there's some doubt as to whether or not that is a Hopf algebra. Are you telling us at this point that actually is a...
No, so I'm asking you, is this a Hopf algebra? That's why I'm saying it's a different thing. It's not the first thing. It might be a Hopf algebra, and if it is a Hopf algebra, can you find the... Yeah. And if it's not a Hopf algebra, then show it to me that it isn't. That's a very good question. So, so here the I
think it's something like the delta has to split it up to things that add up to the same grade, and pi leaves the grade alone, and the m adds the grade back up.
I'm pausing for a second because we have two versions of this, and so you're asking me about this version, the graded version. So in the graded situation, if you're graded and connected, the question is, okay, let me see if I can figure this out. So the question was, if your Bialgebra is graded, does S preserve the grading? And you're making an argument for why that is the case. Which is to say, if you plug in something of homogeneous degree A, then the coproduct splits it into things whose degrees add up to A, and then the coproduct multiplies into degree A. So it is true that this does preserve the grading if it is graded. And so here we see it, for example, here, that this preserves the grading. And so you should see it here. And here, this actually is a Hopf algebra. Okay. So yeah. So hopefully that makes a couple of useful points about Takeuchi's formula. I should say I like this formula a lot, and it's often a valuable tool, and it's often kind of confusing and not the best thing to do. But in particular, you probably realize by now that these are graded connected Bialgebras. And so Takeuchi formula does give you something. And so you should check, is that optimal or not? And if it's not optimal, then can you either simplify it or be clever in some other way? All right. So let me tell you what's next. So in the next few classes, I want to build up our repertoire of Hopf algebras a little bit further. because even though we've seen several examples, I want to show you that we're just scratching the surface and there's a lot more examples. And so we're going to build up a repertoire of Hopf algebras, and in particular, I want to talk next about something called incidence Hopf algebras, which is more general than what we have called incidence Hopf algebras so far. Okay, so, but you know, the building up our encyclopedia of Hopf algebras. Incidence Hopf algebras. So this is something that was anticipated by Joni and Rota. It's an R. And it was really made precise by Schmitt. And by the way, what I'm going to be saying in the next couple of classes is all straight from a paper of Schmitt, which I believe is just called Incidence Hopf algebras. So you can follow along there if you would like. So the idea of this is that it's basically taking these Hopf algebras of posets and making them more general. Okay, and so let me just define. What's a hereditary family? It's a family of finite intervals. And remember, an interval is just a poset with a bottom element and a top element. Which is closed under taking intervals. Yeah. Yeah, when I say 0 and 1, that means that there's a unique minimum element and a unique maximum element. Closed under taking intervals and closed under taking products. Okay, so if a poset is in your family, then every interval in it should be in the family. That's this. And if two posets are in your family, then when you multiply them in the direct product, you should also be in the family. Okay. That's a hereditary family. And you might want to introduce some equivalence relation, the easiest example being isomorphism. Okay, so you might want to introduce an equivalence relation and the most important example is isomorphism. To identify some of these, okay? So what I mean by that is that you might want to say, well, you know, I'm considering all these posets, but let me just say that two of them are the same if they're isomorphic. Okay? And then we want to put a Hopf algebra structure on. So let me call this family script P. You might want to put a Hopf algebra structure on P modulo equivalence. Okay? And so the fact is that you can do this. Okay, so let me write down the proposition of Schmitt that if you have a hereditary family let H of P be the span of the equivalence classes and let me put a subscript to that when I'm so where this equivalence is either isomorphism or more generally what is called a reduced congruence. And okay. Now let me just omit the details of this because really we're going to be thinking of doing this for isomorphism. Okay, but let me just say that there's some other equivalence relations for which this works. Then this is a Hopf algebra. With the following operations. I mean, this shouldn't be a surprise. It's the same operations as before. So the multiplication is to multiply two posets, you take their direct product, which is also in the family. The co-multiplication is that to take the co-product of P, you do the same thing as before. And because these things are closed under taking intervals, this does live in H tensor H. The antipode, this is not trivial, but I mean, we haven't done this before, but we'll do it, and it's easy given that we have Takeuchi now. So we sum over chains, minus 1 to the size of the chain, and then the product of the intervals. Okay. So it's some formula for the antipode. We'll say more about it next time. The unit is that U of 1 gives you the empty poset, and the co-unit is that epsilon of a poset is 1 if the poset has one element and 0 otherwise. Okay? So that's a lot of details, but the point is, given any hereditary family, you are going to get a Hopf algebra. Okay? And the structure is explicit. And so what we'll do next time is explain why this is the case, and use this to build a whole other set of examples that we will use later on. Okay. But this is how to get. Oh, and so the Hopf algebras that arise from this construction are what are called incidence Hopf algebras. Okay. Of course, what the simplest example is to take isomorphism classes of all posets in the world that are finite, and that's what we did, and that was our definition of the incidence Hopf algebra of posets. And you know, this is familiar, but we haven't given a formula for the antipode. So that's the new ingredient, and the other new ingredient is that this works for any hereditary family. Okay? So we'll talk more about the details of this next class and see how it works and do examples.